Hello, welcome back. Today we're going to be talking about the four-wheel alignment. As you may already know, vehicles are manufactured in production facilities in an assembly line type manner. The parts are created and mass produced, so just about every single piece on the vehicle on the next one to the next one to the next one is identical. There are subtle differences that have to be compensated for by having adjustable angles so the tires will track straight with the vehicle, optimize vehicle handling, and prolong tire life. The alignment angles that we discuss are often going to seem exaggerated, and the amount of angle change that is needed in order to have drastic results isn't very much. So when we're talking about these alignment angles, I may illustrate them or show you examples of some of these angles on an exaggerated type of platform, whether that's a race vehicle, a broken vehicle, a heavily modified vehicle, things like that, just to get the point across about what the angle is referring to and where it applies on the vehicle, and some of the wear that can occur because of them. In these exaggerated instances, it's a little bit easier to see visually where and how some of these tire wear angles can affect the tires, and otherwise how they can affect the vehicle's handling. So I'm going to start with this little alignment model car from Hunter and talk about the most important angle that's adjustable on all vehicles. It's the only angle that is required to be adjustable on all vehicles and is sometimes the only one that is available for adjustment, and that's toe. There are two reference points that we're going to use. The first is going to be the geometric center line of the vehicle. The geometric center line is an imaginary line drawn directly through the center of the rear and the front axle passing through the vehicle. The other line is going to be a zero reference line. The zero reference line is represented by a true vertical line. So when we refer to some of these measurements, they may be in reference to a true vertical line or a zero reference line, or the geometric center line of the vehicle. Toe is defined as the distance across the front of two tires compared to the distance across the rear of the same two tires. What that's referring to is the distance across the front of two tires, so this is going to be on the front axle, compared to the distance across the rear of the same two wheels. Referring to toe in that manner is also known as total toe, or you are comparing against one side against the other. Individual toe has to do with using the geometric center line and only referring to one wheel and its relationship to the geometric center line. Individual toe is going to be the distance across the front of a tire to geometric center line compared to the rear of that same wheel or that same tire to the geometric center line. So if those distances are equal to our geometric center line, the distance from the front of the wheel to geometric center line and the distance from the rear of the wheel of the same wheel to geometric center line, if those are equal, it has zero toe. Positive toe is when the front is closer, when the front of the wheel or the front of the tire is closer to geometric center line than the rear. We can exaggerate this like this. So from the front, so the front of the tire is closer to the center line than the rear of the tire is to the geometric center line. This is called positive toe. Negative toe is the opposite, where the front of the tire is farther from the geometric center line and the rear of the same tire is closer to the geometric center line. When you compare it to the other wheel, kind of hard to see in the example here, but this would be considered toe in or positive toe. This would be considered toe out or negative toe. So for real life tires, toe in, the front of the two tires is closer than the rear distance of the same two tires. Toe out, the distance across the front of two tires is farther than the distance across the rear of the same two tires. What's this going to do when you're driving? Well, if we picture a toe-in scenario and the vehicle is going to go straight, the tire is going to be scrubbing partially against the surface in a lateral motion as it rolls. The vehicle is going to prevent these tires from actually joining together on their intended straight paths. And similar to toe out, they're not going to leave the vehicle. The vehicle is a rigid piece. The vehicle is going to keep them all together. So what's going to happen is, let's look at this tire. As the tire is rotating this way, it's also going to be scrubbing along in this motion right here. So if we think about the forces acting on that tire tread coming from the ground this direction, it's going to take this outside edge and start scrubbing it. And so this tire, in an exaggerated manner, is going to be rotating and scrubbing forward. What that means is positive toe is going to show wear, excessive wear on the outer tread of the tires. Because the outer tread of the tire is encountering the ground first due to the direction of the vehicle traveling. Due to the direction of the vehicle travel, take it out. Due to the direction of vehicle travel, the ground is coming this way. The vehicle's going that way. So that road surface is going to contact the outside portion first, and then the tire is going to be scrubbed against that outside surface. So toe in is going to wear the outside of the tires. Now let's look at toe out. Very similar situation here. As toe out occurs, vehicles rolling forward but traveling against the tread of the tire sideways. So the part that's contacting the directional force of the road surface first is the inner tread. So as that tire is scrubbed along its inner tread, that's going to wear the inside of the tire faster. Toe is the most important angle to get dialed in right on the money every time as best as you possibly can. Most other angles can be pretty close to the tolerance. When it comes to toe, many things are dependent on proper toe settings. So toe is going to be the measurement that needs to be dialed down to the 100th of a degree in most cases. Total toe is going to be determined by the combination of both individual toes. Toe is going to be what is used to center the steering wheel. Most vehicles will require a slight toe-in angle. When it's static, we're doing alignments without the vehicle in motion. But when the vehicle is in motion, as it starts to roll, that static measurement of positive toe will usually translate to a dynamic angle, which means when the vehicle is moving, that the bushings and the suspension gets loaded by the movement and ends up being a zero toe situation. Even though the vehicle specification may be positive or not zero, once that vehicle starts moving, it's very likely that the tire angle from the toe specification at the tolerance becomes zero once it starts to roll forward. Total toe, when you combine the two toes together, the two individual toes, will determine which way the steering wheel is going to point. If they are symmetrical, whether they're out of spec positive toe or out of spec negative toe, if they are identical measurements, the steering wheel will remain straight. Your tires are going to scrub bald in a few miles, but hey, everybody loves buying tires, right? What about this scenario? Positive toe on the right, negative toe on the left. Well, it's almost like we're steering the vehicle at this point. But once we start driving, the suspension of the vehicle is going to track the vehicle straight. So the steering is going to equalize once the vehicle starts moving. Once you start moving, those tires go straight, steering wheel equalizes, and is now what was once centered is going to be off center to my right, which will be your left, viewing from that angle. If we had one tire that was 0 degrees, so pointing straight ahead, and the other one was -5 degrees, the steering wheel is going to split the difference. Once the vehicle starts moving, this one's going to move over 2.5 degrees out, and this one's going to move 2.5 degrees in, and our steering wheel is going to be off center this time to my left. When setting the toe measurement, which is the very last adjustment you make on an alignment, adjusting toe is done with the steering wheel locked in most cases. There's a program in the alignment machine that allows you to do this procedure with the steering wheel unlocked, and everything is compensated by the equipment on the alignment machine. You do have to do things in the correct order and follow the prompts, but the machine kind of does some of the work for you. We'll start out by using the steering wheel lock just to get the concept down, doing alignments, that the steering wheel is affected and it needs to remain straight ahead and not deviate. So once we get everything dialed into the proper specification, down to the 100th of a degree on toe, that's going to result in a good alignment. Camber is the next angle I want to discuss. The definition of camber is the inward or outward tilt of the top of the tire in reference to a true vertical line as viewed from the front of the vehicle. So if you're looking head on to the vehicle, and this, let's say the vehicle is where I'm at, and this is the tire. The outward tilt is positive camber. The inward tilt of the top of the tire in reference to true vertical is negative. Using a framer's square. 0 camber is vertical. Positive camber is outward. Negative camber is inward. Camber is a tire wear angle, but it has to do with the pressure on the tire surface that will wear the tire. A little bit, one way or the other, isn't going to drastically affect the tire. And again, I'm talking about angles that are between 0 and 1 degree, plus or minus 1 degree off of 0. What will happen though, in an extreme scenario, which we can actually see nowadays, the amount of pressure at that contact surface with the ground on a very extreme camber setting is going to cause excessive wear on that surface because it is taking more of the vehicle's weight and it's not evenly distributed across the tire. Now, one of the general rules about camber is that a vehicle will tend to pull towards the side with the most positive camber. So remember, positive is when the top of the tire is tilting outward from the vehicle. And that can be illustrated by this. This is an inner bearing race from a tapered roller bearing. See some interesting spalling occurring there. No wonder this was in need of replacement. But a true vertical tire, or a tire with 0 camber, will have an even contact patch across the surface of the tire tread. Positive camber is going to act like a cone. Negative camber does this too, but negative camber, the way that the forces act from the tire tread back to the vehicle, don't influence it as much as positive camber does. So if you notice what that contact patch does to its rolling direction. As the tire is tilted outward, that contact patch with the ground becomes distorted and takes on a conical shape on the contact patch of the tire, resulting in the force acting on the steering and suspension system from that positive camber and influencing the vehicle to pull in that direction. If it was even side to side, there wouldn't be any more pull one way than the other. Excessive out of spec positive camber is going to also wear the tires just like negative camber would too. The only thing is with positive camber or less negative camber, because you can still have two negative cambers, just one is a little less negative than the other, the pull will go towards the side of the more positive or the less negative. So it doesn't always need to be a positive value in order to be more positive. It just needs to be less negative or more positive. And generally what we're looking for is within half of a degree side to side. So our cross camber needs to be less than half of a degree to avoid that steering pole characteristic from performing an alignment. In order to define caster, or the caster angle, we need to first define and understand what the steering axis is, because the caster has to do with the degree tilt of the steering axis. So let's take a look at an example. I'm going to use the McPherson strut as an example for measuring caster. Caster is determined by the steering axis. And the steering axis is an imaginary line drawn through the lower pivot point down here at the ball joint, and an imaginary line up through the top pivot point. So this one pivots up here on the strut bearing and pivots down here on the ball joint. Now that isn't directly in line with the strut body, since our ball joint is over here and our upper pivot is over here. So the steering axis isn't something that you can see just by looking at it or putting up a measuring tool. The steering axis isn't always going to be a vertical pivot point directly in line with the center of the tread. So you might guess where I'm going with this. We can't look at this angle. We can see where it pivots in the steering at the top and at the bottom, and we can imagine the line that is drawn between those two pivoting points, but we can't know what that is for sure. And how are we going to do this on the alignment machine? Well, it's a dynamic angle. So just by looking at it and mounting up the equipment, we cannot tell what the steering axis is just based off of that information. The definition of caster is the forward or rearward tilt of the steering axis in reference to a true vertical line as viewed from the side of the vehicle. So looking at the side of the vehicle, picture a motorcycle. The handlebars are located somewhere behind the front wheel to whatever degree, and the degree that changes can be considered caster, because this is the operating angle of the steering axis. So picture a street bike where the angle is very steep, almost vertical, compared to a modified chopper where it's drawn out and acting on the front tire from a ways back. That would be positive caster. Negative caster would be if we were ahead of the wheel and tilted forward as viewed from the side of the vehicle. So thinking about the forks on a motorcycle is a pretty easy way of understanding it. That imaginary line, that steering axis, is drawn through the pivot points of the steering. So if you know where the pivot points of the steering are, you can look at these areas and you can guess how the system works. And when you're working on caster, if there's an alignment angle that needs to change there, you may have a better idea of how to manipulate that in order to correct the caster angle. More positive caster is going to help the vehicle track straighter. If your caster is too negative, if you get over the steering axis too much, too vertical, it's going to create a wandering effect. A good feature about positive caster is the directional stability. The caster is what helps the vehicle return to straight ahead position. When you let go of the steering wheel and you're moving forward, the wheels want to track back straight and continue on a straight path. If the caster is too negative, there's going to be less motion of the steering to naturally bring the vehicle back to the straight ahead position. Now, too much positive caster is not going to be a good thing. Too much negative caster is not going to be a good thing. The benefit of having zero caster, so you have a true vertical steering axis, is that it's a lot easier to steer. The more positive you go, you're fighting the vehicle's weight over some of that angle. The angle has more to do with where the projected load of the steering and suspension is. So by going positive through those pivoting points, the weight of the vehicle is being projected in front of the tire rather than behind the tire. Thinking back to the motorcycle example, more positive caster is going to result in a truer straight path for the vehicle. The more vertical you get, or the closer to zero you get, it's going to want to wander more. It won't naturally return back to the straight ahead position easily. So think of the chopper versus the street bike. One is more nimble and maneuverable than the other because of that caster angle. There are a lot of other factors that go into it, of course, but the caster angle makes it mechanically more nimble because that steering you're not fighting such an extreme angle on that steering axis. Also, road shock or road feel is going to be a little more pronounced. It'll be a little harsher. With the steeper angle, each bump as that tire rolls across the surface of the road, that bump is acting up on the tire in a vertical motion with vertical force, because the tire contact with the ground is directly at the bottom of the tire, regardless of what the caster angle is. So as the vehicle is traveling, let's give it excessive positive caster. Let's talk about that chopper. That road force is traveling straight up. Well, our steering axis is on an incline. The force acting on that steering axis isn't going to run directly in line with the steering axis. It's going to take that upward force and translate upward into the angle of the steering axis. So it's going to have a harsher feel to it rather than something that is directly in line at 0 degrees. Then you get into negative caster, and the vehicle never wants to return back to center. And it's almost like driving a vehicle in reverse. When you start to turn, the vehicle wants to keep turning sharper because your direction of travel is now making that usually positive caster angle acting the opposite direction. So theoretically it would be negative in reverse. So positive caster has directional stability. Too much positive caster will increase road feel and be harsh through the steering and may jar the chassis of the vehicle to a point where it's harsh for the driver. And negative caster is going to want to be more nimble. So manufacturers will design their systems based off of the purpose of the vehicle and how that vehicle will handle the best with the dimensions of the vehicle chassis itself. The rule on caster is the vehicle will pull to the side with the most negative caster. So if positive caster gives us more of a straight ahead direction, more directional stability, more negative is going to be prone to wander more. If one side of the vehicle is a more negative measurement than the other side of the vehicle, the steering pull will go towards the side with the most negative caster. So steering pull with camber is the most positive camber. Steering pull with caster is the most negative caster. Now the cross caster is the same. We're looking for within 0.5 degrees. So 0.5 degrees, one side to the other. If we're within 0.5 degrees of a difference, then we shouldn't be too concerned about having a steering pull. If we get out of that 0.5 degree cross caster, then we're likely going to have some sort of influence in the means of a pull. And that'll be towards the side with the more negative value. Not that the value itself is negative, just that it is less positive or more negative than the other value. As the vehicle is navigating a turn, the inside wheel that is steering, so the front wheels as they turn, the inside wheel has to turn more than the outside wheel. And just the same when you're turning the opposite direction, the inside wheel making another turn has to travel on a tighter arc than the outside wheel. I'll illustrate this to you with handy dandy variable radius tool, piece of string with a loop in it. Let's take this point here. This is the center point for the radius of each of those arcs. The inside radius is shorter than the outside radius, so it is making a tighter turn compared to the less aggressive turn at the longer radius. So if the vehicle is turning about a point, the inside wheel needs to follow this curve and the outside wheel needs to follow the other curve. The result being, the inside curve is a sharper turn than the outside, so the inside wheel will need to turn sharper than the outside wheel. They'll both turn, but the inside is going to be sharper, and that's what we call, since the front of the two tires is going to be larger than the rear of the same two tires, not parallel, this is going to be toe out on turns. Abbreviated TOOT, or toot. In the PDF slideshow that goes along with the alignment topic, the slideshow will go further into diagnostic angles. So reading from the text, the chapters on alignment, going through some more of these slides that have diagnostic angles will be helpful in the future when you're working in the lab. We're not going to get too deep into that at the moment. I want you to understand the basics of a four-wheel alignment and how that process goes. So I will walk you through that process with a vehicle at the school on an alignment hoist running through the procedure. The part to remember: tire pressure affects it. Do an inspection before getting on the alignment hoist to find any loose or worn components or possibly bent. Road test the vehicle, find out what it's doing before you align it so you have something to compare it to. And the alignment process is going to be rear, camber, and toe. You're likely not going to find a caster angle on the rear unless you have some extreme steering on the rear axle. Rear camber, rear toe. Then you go to the front and you do front camber or caster first. So camber, caster, caster, camber, then toe. So rear camber, toe, front camber, caster, toe. Toe is always the last adjustment that you do per axle, and front toe is the required adjustment on all vehicles produced. So every vehicle has a front toe adjustment because front toe determines the direction of the steering wheel and will affect tire wear the most. Toe out of spec will not cause a pull. It will cause an off-center steering wheel one way or the other. It's not going to cause a pull. Pull will determine, even if you have your toe is set this way, once you start moving, the caster is going to track those tires straight, and as those tires come straight, your steering wheel is going to go off center. It affects the steering wheel position. It doesn't affect the direction of pull. So toe does not affect pull. So let's get to a four-wheel alignment. We'll be on a Subaru Impreza WRX on the Hunter alignment machine. It may be helpful to have somebody spot you when pulling onto the drive-on hoist so the vehicle is centered as best as possible. The different colored extension arms for the alignment heads that attach to the wheel are designed to fit different diameter wheels. Located within the view of the driver is a corresponding color-coded sticker on the alignment hoist where the center of the wheel should be stopped depending on the overall diameter of the wheel. Compact vehicles will have smaller wheels and are blue. Most vehicles fall in the red category, and oversized tires, like trucks and SUVs, tend to be more in the black range. A common practice of safety in a shop: when a vehicle is pulled into the shop, the transmission should be in neutral if it's a manual transmission with the parking brake engaged. On the hoist, the vehicle should be chocked, and the chocks are only necessary on one wheel. and it's best to keep the wheel chocks located near the alignment controls. That way, less time is spent running around the vehicle and walking around the hoist in order to chock and unchock the wheels. The alignment cameras on the aligner are calibrated to read the alignment heads when mounted to the vehicle wheels. The alignment heads are unable to read the aligner heads mounted to the wheels when the hoist is all the way in the down position. So the vehicle needs to be raised up a certain amount in order for the alignment heads to even register with the aligner. So first we will raise the vehicle to a comfortable working height so we can mount the alignment heads and calibrate the system for the vehicle. Whenever working on any hoist, whether it's a drive-on hoist or a hoist with arms, always lower the hoist back onto the locks. The first step will be to set the correct tire pressure. And it looks like we should be at 33 psi in the front and 32 psi in the rear. Here's a nifty feature from this alignment hoist. On the control box, we have controls to set the tire inflation for the front axle and the rear axle. 33 for the front, 32 for the rear. Located near each wheel is a retractable hose assembly. And as we attach all four of these, they will automatically set the tire pressure to the vehicle's specifications. The hoist will automatically set the tire pressure to the desired settings for the front and rear axles. Once this process is complete, they should be disconnected and the valve stem caps should be reinstalled. If the hoses are left on, the machine will stop trying to regulate the pressure, and in doing so will allow air to leak from the wheels through the hose assemblies and the tires will be flat. So when you're done with this step, disconnect the hoses and recoil them back into the retractor assembly. Before mounting the alignment heads, it's important to center the turn plates for the front wheels. The turn plate is designed to pivot on the center and when in the unlocked position can slide around in multiple directions so the alignment adjustments can be made with the vehicle weight on there without the tires limiting how the adjustment is adjusted or how difficult the adjustment is to make. These should remain in the locked position until ready to perform the adjustment on that particular area. So these should be positioned with the center line of the tire by sliding in or outward. As the vehicle is rolled onto the turn plate during the quick compensation, it will already be centered with the tire tread and in an optimal position for the alignment. Do this on both sides. The alignment heads are marked with a label that specifies the location that they're to be mounted on the vehicle. This would be the rear left, this would be the front left, front right, rear right. When mounting the alignment heads, position the arms at the 9 o'clock and 3 o'clock positions and do your best to center them on the wheel visibly. They don't need to be perfect, but close is always better than far off. Once mounted and in a desirable position, lock the tension locks so they have the least chance of moving. The alignment heads have different settings on them. They can be removed while still mounted to the wheel in order to mount different types of adapters for different types of adjustments. Always note the position and the number for each alignment head. And make sure that your position number, in this case 0, matches up with the settings on the side of the alignment head. 0, front axle. On the home screen of the computer for the aligner, open Win Align. Select Begin Alignment, and then enter the vehicle information. Another way of entering vehicle information is to scan the barcode on the VIN plate. This is done with the rechargeable tool and scanning the barcode on the VIN plate. This is a 2013 model. Subaru. Impreza WRX. And we have a notice here that there is a electronic skid control equipped vehicle require the reset of the system after wheel alignment. We'll get more into this later as we cover the automatic systems of the vehicle that are in charge of keeping the vehicle on the road and safe for the driver. For now, we'll focus on the basic four-wheel alignment. The first menu shows our specifications and our tolerance above and below for each measurement. These are decimals of degrees. So we're talking less than a degree of tolerance in either direction. Follow the prompts to mount the sensors. If the aligner cannot see an alignment head mounted to a wheel, there's likely something blocking the view or the vehicle is not raised high enough. An open door is often the cause of blocking a sensor or somebody standing in the way. With the vehicle in neutral and the parking brake disengaged and the ignition unlocked to allow for steering of the vehicle, now we can compensate the alignment heads to the machine. The aligner doesn't know the exact position of the wheels until they're compensated. By rolling the vehicle forward while the cameras are watching the targets on the wheels, they can then calibrate to the position of each wheel. That way, any adjustments that are made can be read by the machine and displayed on the screen. To do this, we'll need to move the car forward on the hoist and onto the turn plate. This is why we're using the label that's on the drive-on hoist. We will unchock the wheels, roll forward, and this will perform the compensation. A lot of the static angles can be measured during the calibration, but angles like caster, which are not visible unless there's motion of the pivoting of the steering, the machine doesn't know exactly what the caster measurement is. So we still need to take further steps to measure certain angles to know where we stand with our alignment angles at the moment. This view has not been a very good one to use. And for me personally, I feel it's because of the amount of clutter and lack of information clarity in order to use this screen. I prefer the bar graphs. You might prefer this screen. But if I'm helping you with an alignment, I'll switch over to the bar graphs because it's a lot more clear to see what's being conveyed through the information on the aligner. Our next step is to measure the caster. Always follow the instructions that the aligner is telling you. It's important to follow all prompts and directions and click to the next step as needed on the aligner in order to get accurate results. Otherwise, you may end up going back into the aligner and having to redo several things that you've done in order to get an accurate measurement. Install the brake pedal depressor, steer the wheels as directed. The brake pedal depressor is being installed to prevent the wheel from turning. Remember, the wheel is on the slip plates, and if we are moving the steering and the wheel rotates on the bearings, then that's going to skew our measurement because the aligner head has already been compensated to its position. So locking the front wheels and making sure they don't turn or rotate during the alignment process is key to keep things consistent and accurate. With the brake pedal depressor installed, we can move on to measure caster. Installing the brake pedal depressor will illuminate the brake lights. These will drain the battery if left on for a long enough period of time. In order to prevent battery from draining too much, a battery charger can be hooked up to the battery during the alignment, or the brake light fuse can be removed to prevent the lights from illuminating. Just remember, it must be reinstalled in order for safe operation of the vehicle once the vehicle is to be released to the customer. Inevitably, this will drain the battery, and sometimes you will have to recharge the battery and you will have to reprogram anything that was lost from memory. Following the directions to measure caster, steer the wheels as directed through the open window, careful not to block the beam, or by manually moving the wheel and pivoting the steering from the wheel. Either way, it's important not to block the beam. Now back at our bar graph view, we can now see where all of our current adjustments are. The four-wheel alignment process should always start at the rear. The rear camber is slightly out of spec and needs to be adjusted before adjusting toe. The alignment procedure goes as follows: rear camber caster toe, front camber caster toe. Most of the time you won't have a caster option for the rear since the rear doesn't normally steer. Some vehicles do. They may have a caster angle. So looking into the adjustments for this, the manufacturer does not specify a rear camber adjustment. The rear adjustment is what sets our thrust angle. Any thrust angle is going to result in the steering wheel being off center by the front trying to follow where the thrust angle is pointing. And the thrust angle is determined by the rear wheels. Our toe is out of spec on the rear. The difference in toe of 0.10 to 0.7 degrees is what's resulting in our thrust angle. The center notch, the center reading, is going to be our optimal point within our specifications. It's important to be in the green zone. It's more important to be accurate to the specification within your tolerances side to side. Before we make any adjustments, we want to make sure that the slip plates are free and not locked. So we're not trying to adjust against the traction of the tire in contact with the hoist. In order to position the front of the tire inward or outward compared to the rear of the same tire, in reference to the opposite side or the geometric center line, this is our toe adjustment. So this is the front of the tire. This is the rear of the tire. We need to control how far out or in the front points. This link here, the cam eccentric, will change the lateral position of this link, which is on this extension here from the knuckle, and we'll pivot that tire in or out as we make the adjustment. This is the nut that loosens and tightens the adjustment. The bolt head on this side is what needs to be rotated. And the bolt is splined to the eccentric on this side and the eccentric on the other side. So the nut does not need to turn with the cam eccentric. So next I will adjust the right rear toe to the specification shown, and then I'll adjust the left rear toe, and hopefully by setting those to the specification, our thrust angle will be 0. Our rear toe measurements are hovering right on and off of the 0.00 degree mark. Notice how our thrust angle is now 0.00 degrees. This means our thrust angle is in direct alignment with our geometric center line of the vehicle. Next, we'll move on to the front axle. We will be adjusting camber, then caster, then toe, because adjusting camber can affect toe, and same with adjusting caster. So toe will be our last adjustment. The illustration for the front camber adjustment is done at the base of where the strut mounts to the steering knuckle. These two bolts, out of these two bolts, the lower one is a pivot point and the other one is a slotted adjustment. So by rotating this cam, it will move the top part the upper portion of this in relation to the bottom portion will pivot like this. And that will affect the inward or outward tilt at the top of the tire in reference to a true vertical line. So this will involve loosening this one so it allows movement of the upper piece, and then loosening the top one and rotating from the bolt head side so both cams are spinning from the front and the rear, and we'll adjust the position of that steering knuckle to get our camber measurement within tolerance or right on specification. With the left front camber adjusted to the specification, we'll see if we can dial in the right side, but at least we're now within our 0.5 degree tolerance on cross camber. After working on the right front side, we were able to improve it by 1/10 of a degree. So at this point, we're close enough within spec, plus our most positive camber is on the left side. We have some road crown that might act in our favor to keep the vehicle tracking straight on most road surfaces. Our caster does not need to be adjusted, and while we're at it, let's just see if there is a caster adjustment available for this vehicle. Does not specify a front caster adjustment. All right. Well, what about? There are no tools defined in the database for the selected vehicle and angle. So with that, we can assume that if we were out of spec significantly, there might be a damaged or bent component somewhere, because there's no way to adjust it and nothing available in the aftermarket as far as a part or a kit in order to gain adjusting ability on the front caster angles. So we'll move on to the toe. For toe, we're going to make additional adjustments and adjust with wind toe. This is a procedure, and it requires following all the prompts in order to do it correctly. Wind toe is a procedure for adjusting individual toe of a steerable axle without locking the steering wheel while making the adjustments. The other way to do this is install the steering wheel locking tool and adjust each the left and the right front toe to the specification, and then double checking it. So let's follow the procedure for leveling and locking the steering wheel. So start the vehicle so we can use the power steering system. We'll give the steering wheel a nice eyeball. Make sure that things line up and that it doesn't look like it's off center. Looks good to me. We'll lock it right there. Engine off. If you notice, our left toe and our right toe are out of spec in the same direction. This one is negative, this one is positive. So the left wheel is pointing out and the right wheel is pointing in. So they're both pointing in the left direction. What this means is that the steering wheel was off center to the right before we centered it. The steering angle sensor is calibrated to the 0 degree position as an input to the systems that use that angle sensor for an input for systems like vehicle stability control, traction control, and in this case, electronic skid control. If we were to skip the calibration after making a mechanical adjustment, our new 0 point from our mechanical adjustment will not match the 0 degree mark calibrated into the angle sensor of the steering wheel. This would input false information for any system using that as an input and would likely result in warning lamps or irregular vehicle behavior when driving the vehicle. It may even cause the vehicle to self-apply the brakes as a safety feature because the vehicle thinks it's making a constant turn while going straight. So now we will move on with the mechanical toe adjustment and get it within spec for our steering wheel position in the straight ahead position. To make it a little easier on myself, I'm going to double click on this left front toe adjustment so that it takes up the entire screen and is easy to see. Sometimes you can select a setting on the aligner to adjust to 0. That may be an option, but the other way is to look at your negative tolerance and your positive tolerance and find the middle point, and that is your ideal specification. In this case, 0 degrees is our midpoint between negative 0.08 and positive 0.08 degrees. So let's adjust this to 0 degrees. First, the jam nut needs to be broken loose from the tie rod end. The outer tie rod end. That was really tight. We'll back the jam nut a little ways off so it doesn't interfere with our adjustment. And now we can make our adjustment by rotating the inner tie rod end on this hex. With the negative toe reading at this wheel, that means it is pointing outward. In order to point it inward, we need to shorten the distance. So while holding the outer tie rod in a neutral position, we will thread the inner tie rod end inward so we get close to our specification. Now, when setting the jam nut, you may be within spec before you set the jam nut, but the jam nut is going to lock the thread. So it's going to take out whatever play there is in the threads. Since I was just bringing this together and I bring the jam nut in and tighten it against the outer piece, against the outer tie rod end, that may take up the slack in the threads in the opposite direction that I made the adjustment. So depending on what your adjustment is, your jam nut will likely affect your overall reading. So you may have to lock it, look at the reading, loosen it, make an adjustment, and lock it again, and do that until you land with it in the locked position at the specification needed. I had a camera malfunction, so I wasn't able to capture all of the adjustment of the toe. But you can see that the toe values are bouncing off of 0. You may not get it exactly to stay there 100% of the time, but as long as it's floating across the 0.00 mark, we want that specification to be adjusted to the 100th of a degree, because that is a tire wear angle, and the most tire wear will occur if that angle is out of spec. Every vehicle has at least a front toe adjustment. It may not have any other adjustment, but front toe is always going to be an adjustable angle. So now we can continue with taking the alignment heads off, and test driving the vehicle will be the final step in the alignment procedure to make sure that there are no pulling, drifting characteristics, that the steering wheel is straight, that nothing is of otherwise concern that would need to be adjusted on the alignment rack. Performing a test drive and a thorough visual inspection prior to setting the vehicle up for alignment is where you'll find loose components or indications of bent or otherwise worn out components like bushings or a bent tie rod or a bent suspension link that could lead to uneven wear on a tire or play in the steering or suspension components. If there is anything loose in the suspension or steering system, that play is going to become apparent when you're trying to make an adjustment, and you may be chasing an adjustment one direction then the other direction across the specification to both outer limits of the tolerance. If this is happening, it's usually an indication that something is loose or bent. If you cannot adjust into spec anywhere close, it's likely bent or broken. And if you keep following either side of the specification without being able to lock it in, that's often an indication that something is loose or worn out. So addressing all these things before you're at the alignment point, before you're at the alignment, will save you time in the future and will help you call the customer only once for necessary repairs and parts and labor. I hope some of the concepts were illustrated more thoroughly through the alignment procedure, and later on we'll address things like the calibration of the steering angle sensor and other steps that were not included in this video. For now, this has been a four-wheel basic alignment and adjusting from the rear to the front of the vehicle, rear camber, caster if applicable, and toe, all if applicable, then front camber, caster, and toe is last in the front. By doing these in the correct order and following the prompts on the system, It will help you accomplish a successful alignment with the fewest number of steps possible, and hopefully will shorten the amount of time that you're tying up an alignment rack, especially in a shop setting where somebody may be waiting to align a vehicle, and especially during normal operation during lab, where other students are wanting to bring a vehicle in to get alignments done. This has been 4-Wheel Alignment. Thank you.